Hi, my name is Łukasz, and today I want to talk about eBPF and its limitations in kernel virtual machine. Before we start, just to mention that we already have a video on eBPF. So if you are new to the topic, I would strongly suggest to watch an introduction, because in this video we'll assume that you have basic knowledge about how BPF works and what is it for. The link will be in the video description. So the plan for today is to do a short recap of the introduction video, especially the flow of how do you go from the source code to running eBPF program in kernel virtual machine. Then I will discuss what's my opinion on how to talk about limitations of eBPF. And spoiler alert, I think the best way is to go through causes of the limitations itself, not the specifics of it. And then we'll go through what's causing the limitations at every stage of the of going from source code to working program. So as I discussed it in an introduction video, you start with source code. It can be any language. Today we'll assume we are using C, and then we compile the source code with C-lang compiler. This combination is the most popular, probably because it was the first compiler and first language supported for eBPF target. That's why we will go with that from now on. But due to generic nature of this video, keep in mind that pretty much whatever, it doesn't matter what language you choose, you still get, you will still probably get the same or similar limitations. Once the program is compiled, we get a bytecode that's loaded to Linux kernel. So we will talk about those steps later on. This slide comes from introduction video, and in that video we also discussed some of the limitations, but keep in mind some of them are already outdated. So why did it happen? This video is about 1 year old, and probably most, if not all, of the limitations discussed then are more or less no longer valid. So there have been a lot of changes in Linux kernel. As we know, kernel development is an ongoing process. There is a lot of changes pushed, and since eBPF is very popular and is getting a lot of attention recently, pretty much every new release of kernel has some changes with eBPF support. So it's hard to discuss hard limitations and say that that's allowed, that's not, because it changes with every release. That's why specifics will become obsolete really fast, as it was with our first video. So today I want to go through causes of limitations for program, and at which step those limitations appear, how we can mitigate them, work around, and what's changing in regards to those limitations. So why is eBPF limited? There are 4 steps. It's my idea how to separate the steps. But first one, in my opinion, it's we have an eBPF target, and this let's say CPU for eBPF VM has limited sets of instructions. Then we go from source code, and we need to compile our source code, and this is depending on which compiler we use and what our compiler can understand, we can get more limited. Then we load the program to the kernel. It's being verified and might be limited at this step as well. And during runtime, we can do as much as kernel allows us to. So it's in other sets of limitations. So from the beginning, we have a limited instruction set. And right now, it's not really a limitation for a developer who is writing the BPF program. One limitation there is that might be difficult to go around is lack of floating point numbers arithmetics. This is because BPF programs are supposed to be deterministic, and floating points are not. So to make sure that a single BPF program will behave exactly the same on each platform, each host CPU, there is no floating point support, and probably there will never be unless the assumptions of BPF change. And this limitation is mostly on people who are implementing VM or the compiler, not really developer for BPF programs, besides the floating points. Next step is compilation. So right now, if we use LLVM CLang, there is not really much limiting us. So everything you can write in C can be compiled by LLVM. So not really much of a difference, but there is no linker for eBPF. So not everything will be allowed. And lack of linker means that we can use global variables, we can use libraries to use functions, but there is no linker to later put it all together. So at this stage, we are not allowed to use, for example, global variables. And this is one of the limitations of eBPF that's very popular and well known. And this is pretty much the reason why for a very long time there was no support for global variables. There were workarounds, like for example, with use of maps. But right now, modern version of libbpf allows us to use, for example, global variables. So this limitations was somehow lifted at this step. Although it's important to remember that libbpf is part of active Linux kernel development. This is a user space library. So the user space library, together with kernel, provides us an address for global variables to be stored in. And we can use them, but it all depends on the version of libbpf we are using. So if you have old enough kernel, there will not be an option to use global variable directly in C code. You still need to work around it, because your version of libbpf may not be able to take over some of the linker job and provide you with global variables support. The same goes for any other limitation that's involved with a lack of linker support. And the next step, during when we use libbpf to load our program, we have kernel verifier. So this is part of Linux kernel that is supposed to make sure that our BPF program is valid and can be run safely. So basic eBPF verifier is supposed to make sure that instruction set is that we are using only valid instructions from eBPF target. And this basically makes sure, like, double checks work of your compiler. So if you are not modifying your bytecode by hand or writing it by hand for some reason, there shouldn't be an issue with that. But kernel verifier builds on top of that, and there is thousands, probably tens of thousands of lines of code that are supposed to guarantee safety of eBPF program. So it's important to know that this virtual machine that we are running in, it's not like regular virtual machine with VirtualBox or QEMU like you would think of. This is a program with different targets, but it's running in kernel space. So in theory, this such program could have access to all of kernel memory and could read and write in places where it's not supposed to. There is no runtime checks of that, like it would be in user space program. So to make sure that we avoid memory corruption, we need to verify the program before it's loaded. And kernel has support for the verifier that makes sure of that. There are no built-in mechanism to work around it. So you need to provide valid bytecode. So this bytecode is analyzed during load to guarantee memory safety and to guarantee it will not hang the kernel by going into infinite loop. So since it's not a process, we cannot kill the process. So in case if we were to, due to programming error, go into infinite loop, this would mean that this program would be stuck running inside of the kernel. And eBPF by design is supposed to be safe, and the verifier is mostly responsible for that. And this imposes limitations like, as you may know, and we cannot use loops in eBPF. This is not exactly true. Right now, you can use loops with modern versions of the kernel. Loops are allowed because verifier tries to make sure that every single path in the program is going to end with return code in reasonable amount of instructions. And this limit changes. I think right now it's 100,000 of instructions. And verifier will, even if your program is safe, but it will, it possibly can take too long to execute. It will be, it will fail verification. There are also kernel functions allowed in BPF programs, so you can call function from the kernel, either BPF helper or function that it's explicitly marked as safe to run from eBPF program, but verifier also makes sure that arguments passed to such functions are meeting the requirements. And we need to remember that verifier analyzes the bytecode during load, so it's not executing the code itself. So it basically enforces programmer to check if the arguments are valid before passing as a function arguments. For example, if we have a function that takes a pointer, this pointer for that particular function may be marked as it cannot be a null pointer. So the function will not check it inside. So we need to do this before calling such function. So with this function calls, important thing to note, which is also a limitation of sort, is that eBPF, when we write eBPF program, we need to provide a license. It doesn't have to be a license file, but we need to set the license inside of the code. And if this license is not GPL, our set of function calls from the kernel is limited to those functions that are not licensed under GPL, because it would be in conflict with the with license your code is distributed with. So only GPL based eBPF programs can use full set of tools provided by the kernel. If you are not using GPL, you need to re-implement those functions yourself instead of using kernel ones. Okay, that would be all for today. Thank you for sticking with me. eBPF is assumed to be a very boring topic, so great you managed to get to the end. If I had something wrong or you have additional questions, feel free to contact us or to leave a comment under the video. Thank you.